Here's the equation we wrote last week for constant acceleration. Let's add the subscript x to show the velocity and the acceleration are in the x direction. Here's the analogous equation for the y direction. We'll use x for horizontal and y for vertical. As you saw, for a dropped object, there's no x velocity, vx0 equals 0, and no x acceleration, ax equals 0. And if we release it from rest, then the initial y velocity is 0 too, vy0 equals 0. Here, we're only interested in the y motion. Let's measure vertical position y from the floor. So the ball hits the floor when y equals 0. Using ay equals minus g, the time when it hits the floor satisfies 0 equals y0 minus half gt squared. So, half gt squared equals y0. Rearranging, we see that the square of the falling time is 2y0 over g, so the falling time is proportional to the square root of the initial height. So, assuming constant acceleration, if we double y0, we increase the falling time by root 2, or a factor of about 1.4. If we increase the initial height by 2 squared, i.e. a factor of 4, then the fall time increases by a factor of 2. And if we increased it by 3 squared, i.e. by 9, then the fall time would increase by a factor of 3. That's interesting. Continuing that series will give us a simple way to measure g and also to see whether it's constant. On this string, there's a mass at position 0. Call it mass number 0. Then mass 1 is at a height of 15 centimetres, and we'll call that L. Mass 2 is at 4L, that's 2 squared times L, so it will take twice as long to fall. Mass 3 is at 9 times L, mass 4 at 16L. In other words, y equals n squared L, where n is the number of the mass. Substitute this for y0, the initial height, then take the n outside the square root. Now we have time to fall is proportional to the number of the ball. They should land equally spaced in time.